error or the mismatch in the data. Okay. So that is the p-slave error based on the read data. See here. It compared the read data and the write data.
Okay.
So today we'll see the SystemVerilog program of APB. Okay, actually we have, as per the schedule, both SystemVerilog and UVM for the verification protocols, right? So APB we are going to discuss in SystemVerilog, AHB in UVM, and AXI in the UVM. Okay, so today we will go through the SystemVerilog test bench, how to design for APB protocol. Okay, meanwhile, I will ask you the few questions in APB protocol. Okay, so can you tell me the bandwidth of APB, AHB, and AXI? Have you gone through that? Anyone? Have you searched for the bandwidth of APB at under what bandwidth the APB protocol will work, and AHB and AXI?
I think AHB's maximum is 128 bits.
Okay.
AHB is 1024, and not having knowledge about
What
Excel.
is the clock speed of APB? At what clock speed it will work? Okay. So how many phases it will take to complete one transfer? How many cycles?
It is
Cycle for each.
Each cycle for each transfer?
Cycle for each transfer, minimum.
4 cycles, 4.
Minimum 2 cycles. Okay. Setup phase and the access phase. Minimum 2 cycles are required. Okay. So what are the different phases are there in APB?
We have initial setup, access.
Okay.
3 phases, I think.
setup and access.
Okay. So what is the difference between pre-protect signal and p-slave error in APB?
P-error signal is the error, the signal which is difference from revert back from the slave side, slave block.
Okay.
Am I right or wrong?
Yeah, right. So P-ready signal in the sense it should get the output from the slave, because slave need to respond to the master, right? That's why. And
There can be multiple P selection, but only one P slave error.
P selection is for slaves, for selecting number of slave. Okay, at a time we can send the data to one slave only, not multiple slaves. From one master.
But we can have,
slave.
like, let's say we have 5 slaves. So we can have 5 P select lines, but we will only have one P slave error line.
Yeah. So P slave error in the sense it will get the output by checking the master read data and the slave read data. Okay, if there is any mismatch in the data, the P slave error will be high, so that we can check the error.
Okay.
Yeah. So I think everyone understood about the specification of APB protocol, right? So APB protocol is a very like a very little, like small only. Okay, you can understand the topics easily. Mainly the finite state mission. Okay, so by using same finite state mission, we will write the program for APB here. Like if you go to yacht have some finite state mission, and it have separate transmitter and receiver block. And I2C have some separate frame format, right? So based on the frame format, we can write like that. In APB also we have the finite state mission. We can design by using the finite state mission. Okay. So if you want to write a sample program, how you will write a sample program for APB protocol?
First, we will have the events for different states.
Okay.
And then we
Simple
will.
So based on the states, how you can write the final state mission as a design, how you will consider the design program here.
So in the
I think
beginning,
we
it
can
will
use
be.
enumeration.
Okay.
The number of input and the output signals from the finite FSM, and the states by which we can write the RTL program.
Okay.
Yeah.
That's what I'm telling. How can you write the program? Have you not tried? You got 2 days time, right?
Ma'am, we will have a 3 state.
Ma'am, ma'am,
satisfied.
I just had a small doubt. Can I
Yeah.
ask?
Yes, tell.
Basically, for APB protocol, it's like an interface, right?
Hmm.
So, so it is like acting. If I say a driver BFM, it is sending the data through this APB protocol to the DUT, right?
Hmm.
That's
Yeah.
what, right? So,
Yeah.
so if I want to design an APB protocol, so so this is an interface, like you can't make these are the input signals, these are the output signals. It is like getting access from both the master BFM and taking the response from the slave BFM. So how can we say like exactly this is the input for an interface, this is the output for an interface?
Because if you are sending a master, suppose here you have a processor or there is a memory. Okay, so memory always we will connect a AXI. Suppose here AXI is there or APB is
Hmm.
AHB is there. AHB to APB
Hmm.
bridge will be there. Okay, so all AHB
Hmm.
signals will be converted to the APB signals via bridge. Okay, so if you take
Yeah.
this memory, what is
Hmm.
the performance, how the memory will work? It have some write data or some read data. So that write data and read data, it is sending the AHB master. Okay, so master is going to
Yes.
take that data of memory, and whatever, if you
Hmm.
are, if you want to interconnect a memory with some other RAM or some other any like any
No,
accelerator,
no, just a
small
small,
program.
so here,
uh,
if you say, just a minute, ma'am, small doubt. So here, if you say you are taking a memory, you
hmm,
are taking some write data signals and write data signals, and you are passing through the interface AHB, and
yes,
this interface is passing through a slave, right?
yes,
Let us consider it is not have, it's a simple design testing. So it
okay,
is simple transfer, like AHB is transferring to another DUT, right?
okay,
So the DUT should respond back with another signal, which is an output to that slave signal. If I say another memory is there here for AHB, it is transferring this memory one signals to memory two signals, right?
okay.
Can you tell me, can you help me to share my
Suppose
screen?
here
Like
there
I'll
is a
draw and
memory
explain.
one. Okay, here there is a memory
Yeah,
two.
you memory two.
Yeah,
So these AHB signals are directly going to this memory two. You
okay,
can send the signals yeah,
okay,
from the AHB, and then also from memory two, you are getting a response signals back to this AHB, right?
mm, yes,
Like if I say like the right transaction is completed, then like let me say the make a response like that, not in AHB. I'm saying like some, let us consider an AXI. So it will be having a response signal, right?
okay,
Uh, so if I say like I am having a response signal for
mm,
AHB, if I say, how can you define this is an input to an AHB? This is, if I say for master, we can say like write
mm,
address, write data, and write enable are the inputs, and like you are reading the data from particular for particular read address data. So that will be an output data. We can define like this is an input signal, this is an output signal. But for AHB, it is collecting the signals from master one and transferring to master two, and it is also taking the signals, response signals from master 2 and also transferring it to master 1, right?
Yes.
So then how can you define like this is a particular input signal for AHB, this is particular output signal for AHB? That's the
Okay,
question
you
that I
want to
wanted to
talk
ask.
with only AHB. You don't want to take any bridge or
Yes.
converters here. You just want to take.
No, I don't want to. I just a basic. So
Okay.
this example is like
So here
when I test
memory
like a
1 and
BSF. Yeah,
memory
yeah,
2
yeah.
is there. Okay, so two memories
Hmm,
are
hmm,
there. Like you can consider this
hmm,
memory as a FIFO memory, and here also another FIFO
hmm,
memory and or a RAM memory. Okay, so here
hmm, hmm,
whatever the output or getting here from the memory,
hmm,
directly we can connect with
hmm.
the interface, APB interface.
Yes.
Okay,
Okay.
so APB interface, when you are doing the right transaction, so this master will work
Hmm.
as a slave. Whatever this block, this memory will work as a master, and this memory will work as a slave. It purely depends on the
Yes.
design, and sometimes this memory can
Yes.
act as a master, and this memory can act as a slave. Okay, based
Yes.
on
Yeah.
how you are connecting. Okay, so both can
Hmm.
access,
Hmm.
both can be work as a master and slave. We cannot decide that as per
Yes.
the specification, as per the design engineer specification, we can do that thing. Okay, so accordingly,
Yes.
whenever it is a master, automatically it will be a slave, because the signal we are passing the
Yes.
data, we are selecting this particular slave from the select or any address. Okay, suppose if you are considering
Yes.
this as a slave 1, and there is
Hmm.
another type of
Hmm.
slave 2, another type of
Hmm.
slave 3, each slaves have some
Hmm.
particular address. Based on that address, we are
Hmm.
going to pass the data.
Yes. So for APB, this is passing the data from master 1 to master 2, right? So
Mm.
for APB, you consider the signals that are coming from master 1 as input signals or output signals
Here, for APB, these signals will be the input
while designing
signal.
an APB. While
Uh,
designing an
by
APB,
designing an
how can you
APB,
consider those signals?
these signals will be the
Hmm.
inputs to the from the master 1, and we
Yeah.
want to send this master 1 data to the master 2, right? So
Yes.
how we will get
Hmm.
that thing? Here there will be write data and
Hmm.
some write operation, write or read,
Address, right address. Yeah. Yeah.
write address. So these
Hmm.
things will be there this side. Okay, automatically the
Hmm.
APB protocol will get write data, write and read signal, whether it is read or write operation, write address, and at a time it also have the slave select signal of slave. So based on this select
Yes.
signal, what happens, that particular address will be transferred to the particular slave of here. So here it will
Yes.
get the read address. According to your design program, you need to write the design program. So here you will get the read data, read address. In that particular read address, it will store the read address. In that particular data, it will store the write data into the read data based on the slave select, based on the select signal. Then what happens? These will be the input signals. Wait.
Ma'am, one doubt
So
here.
these will be the input signals, and here these will be the output signals, slave signals. So again, the slave need
Hmm.
to send the response to the master. Here we have the response as
Master.
the P protect signal and the P slave error. But if you go for
Yes.
AHB or like that, there we have the split transactions, read write transactions,
Yes.
and if you go in terms of burst signals, there we have different responses, B response or response. Those type of responses will be there
Hmm.
if you
Hmm.
go for egg side.
Hmm.
Okay, but here we will
Hmm.
have only P slave error and the uh,
Yes.
protect signal. Okay, protect signal in the
Hmm.
sense, the if the master is not able to take the transaction because it is in other transfer, it is in busy state, so that it will send the P protect signal. That is one, if it is in busy transaction.
Yes, ma'am. Like
Otherwise,
just a minute here. Yes,
hmm,
ma'am. So it is taking input signals, write data, write address, write enabled, right, from
hmm,
master one. So you are saying like those are the input signals for APB.
hmm.
What I'm saying is it is also sending these input signals to the output master two. Then how can you say like these are the input signals? Because these signals are acting as an output signals, right? For the master two. So you can't say like this is the input signal for APP. So it is taking from master 1, but it is also transferring it to master 2, right? It is acting as
Yes.
an output signal as well, right?
Yes.
See, for this master, it is acting as
Sir,
a output
for
signal.
that master,
For APB master, those are
no.
the inputs.
And it is
Okay,
also
ma'am.
transferring these inputs to the master 2. So it is taking the inputs from master 1 and it is transferring to master 2, right?
Okay,
The
if you
input
consider
signals
this
from
as a
master 1.
master 2, see, if you consider this as a
Hmm.
master again, those will be the input signal for
Hmm.
this master. Wait, I will
Yeah,
show.
then the output signals, yeah.
Here there is a master 1, master 2, master 3, master 4. Maybe sometimes it will
Yes.
work as a master and slave. If you want to send the data
Hmm.
from these two, that will be the master and this will be the slave. Suppose if you want to send the data from this master, this block to this block, then it will initiate the transfer, and here this block 1, 2, 3. Third block will act as a
Yes.
slave and second block will act as a master. And if you want to transfer the
Yes.
data from third block to fourth block, here third block will act as a master because it is initiating the transfer. Fourth block will act as a slave because it need to take the data from the third block. These blocks will be any digital blocks.
Yes, ma'am. Like I got the point. Like
Mm.
when these masters and slaves, I'm not telling about these masters and slaves. I'm telling about the interface. Like it is
Interface
taking
input signals is depend on whether whenever they are acting as a master, those will be the
what
input signal.
I just want to add a point, ma'am. Like
Mm.
what I think is like we add the logic signals instead of inputs and outputs in an interface. Is that
Mm.
fine? Like we can't define like it is an input, it is an output for an interface.
Yeah, no,
So I
we
add a
can't
logic
define,
signal.
we can't define whether it is a input or output. Based on the
Yes, that's
requirement, we
why.
will
Yeah,
take.
that.
Yes.
So we add the logic signals in an interface instead of inputs and outputs. Is that the exact thing? What is happening in an interface?
You want to add logic signals.
Instead of writing an input bit 32 data, I'll take
Okay.
logic bit 32 data.
Okay, logic
So
32
it
data.
can
But
take according to.
In
It
sorry
verification,
to
can take
we
interrupt.
don't.
accordingly, like whether it can be an input or it can be an output, right?
Yes, yes. In verification, we
Yeah.
will take in the same way. Yeah, tell.
But logic cannot be used as a in-out,
No,
right?
we can't use. Logic
Yes.
So
we
that's why,
can.
like, because an interface, like, it is taking the inputs from master and it is transferring the same inputs as an output signals to the slave.
Mm.
So we can't say like these input signals, these are the input signals for the interface, these are the output signals for the
Mm.
interface. So
Yeah.
that's why I think the logic signals are added in the interface. Is that
Yes.
the
Yes, that's
thing?
why only. Because if you don't have
Okay.
logic, what happens? We need to write particularly which one is the input and which one is the output port. Okay, sometimes there will
Yes.
be some
Okay.
procedural assignment and sometimes there will be continuous assignments also. So in high level program, we can't check all these things, right? Instead of that, we are using the
Mm.
logic. No need to bother about
Okay.
what
Okay.
are the
Okay.
inputs and what are the outputs, which type of blocking, which type of description style we are using.
Okay. Okay. Yeah. Okay, ma'am. Thank you.
Yeah.
So, ma'am,
Okay.
there will be two interface in this case, right? Like, for example, from the master perspective, uh, mm, so one is from the master perspective. Okay, can we have a whiteboard, please? Like, can we just have a whiteboard so that, like,
Okay. So it is also
it's-
white only, right?
okay, okay. So yeah, so we have a master. I think this is already discussed. Just want to clarify from my end, just so that I'm not missing anything. So we have master here, that is 1, and we have a slave, that is 2.
Okay.
So between 1 and 2, there is an interface, which is an APB interface, right? Between 1 and 2, there is an interface, which is an APB interface. So now, can you draw that interface, ma'am, between 1 and 2? APB? Yeah. So this is an APB interface between 1 and 2. So now this APB interface has something as input, and it has the same, whatever there is coming as input, it has the same output. So like P selection. So master is sending P select, read write address, data, and so on. So same thing is going at the output of APB towards the slave.
Okay.
And
That's
right,
why
is
we
the
are writing
slave.
the as logic instead of writing as an input or output to the
Right,
APB protocol.
right. So that's how we are, that's the right understanding, ma'am. The output is the same, right? Output of this is the same,
Yes.
APB.
Yes. So there will be no input and outputs for the interface. That's what I think is like.
Hello?
It is just a transferring bunch of signals from master to slave and
Yeah.
collecting the response signals from slave to master. It is just a bunch of signals adding up. Like it
Yes.
doesn't define the
One
direction like
question in this
inputs or
case
outputs.
is one question in this case. So the master has to be APB aware that okay that this master should know all these signals what APB understands, right?
Yes.
So master has to be APB aware then.
Yes.
So
So
then
whatever
only it
the
can send
No,
master,
we
these
can
signals.
see,
transfer the data.
internally there
Yes.
will be, yeah, internally there will be lot of signal interface interconnections will be there. Okay, whatever we are seeing here, just block level, it doesn't happen actual SOC or if you take any IP level. Internally there will be sub connections will be there for each master design to the APB design. Actually, we will have the APB designs here. We are just telling APB protocol master slave, but if you go practically, we will have the UBCs. Actually, we don't have actual APB or AHB or AXI designs. We don't have. Just we'll create some UVC. Okay, so UVC is nothing but it is a component, verification component. Okay, through the verification component, we can send the data. So whenever you are creating verification component, what happens? Currently in every SOC we are using AXI only, right? So all AXIs, whoever the IP vendors or VIP vendors are there, they will have the common logic for all AXI. Okay, so internally there will be lot of signals for connecting our own master to the AXI signals or APB signals. Whatever we are seeing here, just P slave error, these are not. Internally there will be lot of signals for interconnection.
Okay, ma'am, the reason I was thinking this because according to me, no, there are so many wires here. From master to APB, there are so many wires, then from APB to slave. So I was thinking master, why not master send just one address signal to APB? APB then resolves, okay, this address belongs to this selection signal, and then it sending the output to the slave. So this way we'll save so many of wires, something like that.
Yeah,
So okay,
That
we
is an
can.
AXI based AXI.
In
AXI is
AXI
that
you are
that's
talking, huh?
what AXI do.
no,
No, he's
okay,
saying like to implement an AXI in APB. It's a spec,
Mhm.
bro. Like we can implement that your spec in AXI.
okay, so you mean that whatever I'm saying
Instead, like
is implemented in AXI and not
AXI,
in
yes,
okay,
that's what
I was not
AXI
aware
does.
of
Like
AXI.
AXI, yeah, in AXI, starting address will be taking, and then the slave itself will be decoding the addresses from the like
Hmm.
from the starting address through the burst. Like there will be some burst type, like burst length and burst size. Through that, it will be decoding the starting address and these things, and then it will be transferring the data. Yeah, that's your. It can be done in AXI. That's a
Okay,
spec.
okay, makes sense. Then we can save wires, right? So okay, thanks. Thank you.
Okay, yeah. So I think everyone clear with spec, right? So once you will get to APB and all, you will get some clarity. Okay, so this is very basic, right? Basic program, basic protocol, right? So that's why very less number of signals. And tomorrow, before coming to the session, okay, just go through the AHB because we have 2 days for AHB. One day we need to discuss overall UVM environment. One day is for theory. Okay, so tomorrow we can't cover overall theory, so just go. That's why I have shared yesterday only because today is Sunday, right? Maybe you will go through that spec. That's why I have shared yesterday only. Before coming to the session, you need to go through the entire like just signals. What are the input signals and what are the output signals? Just go through those things. Okay. And there are transfers are there, different type of transfers are there. Okay, transfers we will discuss tomorrow, chapter 3. Transfers we will discuss. Otherwise, after the session, I will tell. Okay, I will plan and I will tell how you can learn those things. Okay, because I have already uploaded some sessions, AHB sessions in the YouTube. Transfers will cover in that session. If you go through all the transfers, we can discuss something other topics, right? Because session is already available in the YouTube. So I will let you know after the session what you need to learn. Okay. Okay, first of all, if you all clear with the AHB specification, we will go through the programming now. So here, if you see whatever we have discussed yesterday, there is a transfer. Okay, if you have idea of writing the protocol, the waveform by using the waveform, I mean by using the finite state mission, you can write very easily. This waveform is nothing but the finite state mission only, right? So whatever the T0 is there, T0 is nothing but ideal phase, T1 is nothing but setup phase, T2 is nothing but access phase. So in each phase, what happening here, that's what we discussed yesterday. Same thing you need to apply in the programming. Okay, by using the finite state mission, you can take the state here, ideal state. So if you are in ideal state, what is the output logic and what is the next state? If you are in setup state, what is the output logic and what is the next state? If you are in access state, what is the output logic and what is the next state, and what control signals you need to take? Based on the control signals only, we can initiate the address or data, all these things, right? So those things we'll discuss. There are very
Ma'am, just a
different
minute. I
coding
got
styles will
just
there.
a small,
Yes, Stav. Yes,
ma'am,
Stav.
a small dot. Sorry to disturb you. Like you can open that waveform, right? The wait state waveform with wait state waveform.
Okay.
Uh, so here, what I thought is like all these are like logic signals for APB, right? These can be like they, all these are like logic signals. There is no input signal, there is no output signal for APB,
Yes.
right?
Yes.
So while designing,
While
so
interfacing.
here, just a minute, ma'am. He's saying like that T3 to T4 cycle is a wait state, right? T3 to
T3 to
T4 is a
T4. Yeah, in this it
T4
is a
is a
wait
wait
state.
state, right?
Yes.
So he designed in a such a way like it is unnecessarily wasting one clock cycle, right? While designing with a wait state.
Okay.
So what I'm saying is like I'll write an assertion like whenever my P ready is valid, after before 2 clock cycles, you make the address and write available so that this T3 to T4 clock cycle will be not wasting the clock cycle. So that it will be improving the latency or improving the it reduces the latency of the APB protocol.
Yeah, we can use assertions in the design. We can write the
Yes,
by using the assertion so that
why exactly he is using this wait state then? Like, what is the reason of this wait state? Like, we
see,
can implement
what is
the
the reason to
APB state.
okay.
Yeah.
See, even if you use the assertion, can you change this spec? I mean, the main motive of this periodic signal.
Yeah, this is wasting a cycle. So everyone wants the like
Why it is
as a
wasting a
designer.
cycle? In this cycle,
Yes,
something
because
is
it's taking
some
just a minute.
operation is going on with the slave. If you are doing the
No,
write
ma'am. Like what
transfer or from at the read transfer side, something is going on. That's why it is in waiting the state. That is the disadvantage with the APB protocol. But if you go for AX side,
so
you no need to wait for the until slave complete. We can transfer all the transfers at a time. No need to wait for next until the slave complete.
So, Madhukar, just a question to you. How do you come to know that writing takes only one time cycle?
no, not writing takes. It's taking two. It can take two clock cycles, like access phase and the
So, so the
setup phase and the
counter
access
question is,
phase.
so the counter question is, suppose if you are writing in some particular memory address, and then in next cycle
Hmm.
again you have to write in that same memory address. So until unless
Yes.
the
Okay.
operation has been completely done on the particular memory address, how can you transfer next data for the same memory address? So,
So I'll say for the master, like you wait for the ready signal so that whenever the ready is one, then only you send before 2 clock cycles the address and write values, so that it
But master
will not
cannot
waste
predict.
this T3 to T4 clock cycle.
But I
One
think
clock
Madhukar,
cycle.
master cannot predict when the period will be, like, because master is different entity and slave is different entity, and slave is doing some transfer for some another master. So master one might not know, right? Like when period will be.
Yeah, that's a point. Yeah, yeah, yeah.
I think
Okay, thank you. Yeah,
there is
that's a point.
nothing
That's a
like
valid point.
which,
Yes, yes, yes.
hello,
Yeah. Tell.
hello.
Hello.
I think there is nothing like a wasting of clock cycle. It is like a additional features in the ABB protocol. Like
Yes.
there be maybe a many scenario where we want to hold our right, so we can extend the transfers.
This is not compulsory. This is not compulsory. We have without wait state also. That means without wait state, we are not doing any other operation in the current time. So directly we can pass the data. But whenever we are the slave or master is busy, then it is a separate like advantage. It is a separate feature which can be wait for some time to transfer next to make next transfer.
Oh yes, it's an additional feature. Yes.
Okay, this feature we don't have in AHB and AXI, because in AXI we can directly make the transfers without waiting for any operation to complete. Okay. The freshers, are you understanding?
Yes, ma'am, we can proceed.
Yeah, okay.
Hello, ma'am.
We'll write the program for APB slave. Okay, so this is the
Hello.
simple, yeah, hello.
Hello, ma'am. The verification will be based on the UVM or on the SystemVerilog?
For APB, we are seeing SystemVerilog. From UVM, we can verify using, sorry, from AHP, AXI, we can use the UVM.
Okay. Today is the APB APB, na?
SystemVerilog. Yes, yes.
Okay. Okay.
Okay, see here. First, we will write the APB slave as a design. From APB master, we will initiate the transfers. Okay, so here master is applying the stimulus. We are not designing both the APB master and APB slave. Okay, so here we are designing APB slave as a design and APB master as a verification. Okay, so module slave clock reset. And you know all these signals, right? No need to explain. Address, write data, read data, write, p enable, p ready, and p select. So all are declaring as a inputs here, and output p ready and p read data. Because for the slave, all these data will be as a input, and p ready will be the output, and p ready and p read data will be the output.
So
P
P
slave
slave error should
error
also.
we didn't use in this program. So if you are interested, you can add. Just you can check with the scoreboard logic. Okay, the design output and whatever the output you got, you can write the logic. Okay.
Oh, okay. Thanks.
Next, present state and the next state. You already know these all things, right? Ideal setup, access, and access wait state. 4 states we are declaring, and always at the rate of pausage clock, negate reset, active low reset, and it's asynchronous. If reset is high, present state will be ideal, otherwise next state. So in the ideal state, suppose if the present state is ideal state, based on the p select signal, next state will be the setup state. If p select is high, then next state will be setup, else next state will be ideal state. And if setup phase, if you are in setup phase, next phase is access phase. And if you are in access phase, it will depend on both P select signal and the P ready signal. So if P ready signal is high, and if P select signal is equal to 0, then it will be ideal state. Okay, because P select equal to 0 means we are not initiating any transfer to the slave. Okay, so it is 0. And next phase will be the setup phase. Otherwise, if P select is high, next phase will be the access, next state will be the access state if P ready is 0. And access wait state. So whenever you are in access state, you need to check with the access wait also based on the P ready signal, right? If P ready signal is high, next state will be the access. That means we need to wait for the until it complete the transfer. So if P ready is 0, no need to wait for the wait for any operation. So we can go for access wait state, and by default next state will be ideal state. Okay, so can you
Ma'am,
all,
just a minute. Can
okay,
you just a minute?
just a
Sorry, ma'am.
minute, can you
Can you
please
go?
join for the next session, everyone, quickly?
Okay.
Yes.
Yeah, in the session. Okay, so here master we need to initiate, through the master we need to initiate the transfer. Okay, so here we have the APB slave.test also, direct APB direct Verilog test bench. See simple Verilog test bench. Here read clock, we have taken 2 clocks and reset P address, P write data. It is not important. Okay, you can just go through this. We are passing the write data and the address, and passing the read address. Okay, 12, 22, 13, 23, 14, 24. We are passing write data and read address here. And next, we'll see from the interface onwards. Okay, so in the if you go to SystemVerilog architecture, we have the, can you tell me what are the blocks we have in SystemVerilog? Generator, driver, monitor, scoreboard, and the driver will be
Reference mode.
interconnected with a DUT via virtual interface, and through the virtual interface to monitor here to the scoreboard and top level environment, and then top level test, and then top level testbench.v or SV. So this is the SystemVerilog architecture. So first we will start with the interface. So here all will be declared, all variables are declared with a logic data type. You know why we use in the SystemVerilog. So next, clocking block. I think no need to explain the clocking block, right? So whatever the outputs, the driver inputs are there, we will declare as a outputs here. DUT, output, address, write data, write, select, enable, read, read data, and the P ready or the inputs. Okay, so here reverse, because all the DUT data, because here the DUT is connecting to the monitor like this. That means all the output of whatever it is generating the variables, all those signals will be the inputs to the monitor. That's why here all these are inputs. And modport driver. So modport driver, we will include this clocking block driver here. That means all these signals will be included here, and clock input, clock reset. And same monitor modport, here clocking block modport CB, we need to include the clocking block and input clock reset. So this is simply how we can write the interface. I think no need to explain what is meant by clocking block, modport, all these things, right? Next is a transaction. Transaction class, here we need to randomize all the input data. So what are the inputs are there here? P address, P write data, P write, P select, P enable. All these are inputs, and P read data and P ready are the output. So no need to do the randomization. That's why we didn't declare as a ran data type. And next, constraints. We are writing the constraints here. So I think you know already what are the different types of constraints out there and what is meant by constraint, right? So here P address. For P address, we want to generate only between 10 to 20. Okay, if you don't use the constraint, what happened? Whatever the 32-bit size here, the same 32-bit size will be 32-bit size will be generated. Okay. So whatever the particular scenario you want to generate, we can generate through the constraint. Like the p write data, we are generating 50 to 100. And here is the function display statement. So we can display p write, p address, p write data, p read data, all these statements. Okay. So this is the transaction class and the generator class. In the generator class generator ran transaction, mailbox, function new, task main, repeat of 10 times. And we have created the object for transaction class and doing the randomization by using the randomize method and sending the data to the mailbox. So tr.display of generator. Actually, this is very simple program. If you want to learn the complex program in UVM, I will share the UVM code also after the session. Okay, so because of first session, I'm just discussing simply for APB. But from tomorrow for AHB and AXA, we'll discuss in UVM, so you will understand each scenario. For APB also, if you want, I will share the UVM code. Okay. So this is the main task in the generator, randomization and just sending the data to the mailbox. And driver. So in the driver, so you know this path, right? Tick define, dribf is the name of that macro, and APB-VIF. APB-VIF is the virtual interface. Virtual interface dot driver clocking block. Why we are using the virtual interface? Because of interface is a static in nature. As we are using the class-based verification, it doesn't support the static, right? Because class-based verification means all those components work as a dynamic in nature. That's why here we are creating one virtual interface because it is a dynamic in nature. Okay, so we are connecting our virtual interface to the main driver. Okay, so clocking block of driver CB. So this is the path we can write for that. And class driver virtual interface. We are creating the virtual interface. APB interf is the name of the normal interface. For that, if you create as a virtual APB interf, APB VIF is the virtual interface name. Okay. And mailbox generator to driver and transaction TR, we are creating the object for transaction. And what is the constructor here? Why we need to write the constructor for SystemVerilog? And what you will write for UVM in place of new function constructor?
Allocate the
Create.
memory, right?
Okay.
In UVM, we will have build phase where we will create the use create for.
Here we are like connecting the virtual interface with the static interface using new method from the test.
Okay. So actually, whatever we are using, either it is a component or it is a object, we need to create. Okay. Suppose here we are using the class driver. So driver need to create. And also, if you see here object, in generator, we have used the new method, right, for creating the object. TR is the object of the transaction class. So whenever you are taking a driver or generator, whether it is a component or a object, you need to create. So object, we use the new method to create, but for components, we use the function new to create the memory. Just we'll just create the memory. Okay. But here in SystemVerilog, we use the new method, but whereas in UVM, we use the create method because of few disadvantages of new method. What are the disadvantages of new method? Like it doesn't, whenever you are taking different class variable class names, so we cannot do the overriding. That's why we use the create method. That is a different topic we can discuss in the UVM. So these are the connections. Okay, so there is a driver and there is a DUT. For generator, what are the connections will be there? For generator only the mailbox connection will be there, right? But for driver, the mailbox connection will be there and also virtual interface connection will be there. That's why we need to pass virtual interface and also mailbox. Okay. But here if you see in generator, we will pass only mailbox because one connection for the generator. Like that, for driver, you can use many one or two mailboxes, like generator to driver or driver to scoreboard mailbox, like that. So you can make more connection, like one more connection for the scoreboard. And this is the function how to write. And task, reset task. Reset task in the sense we need to do the reset for all variables, right? So reset started and reset ended. Okay, if you see here, tick drivf dot p write equal to 0. What is the drivf? Nothing but whatever the DUT signals are there, we are connecting through this macro, right? So already we have mentioned the path here, right? We are connecting through that macro. If you don't write the macro, what we need to do? You need to copy entire this path. Through this path only you can you can make the connection. Okay, you can pass these values through the connection. Next,
One
task
question, please.
drive. Yes.
One doubt. Why did we use, this non-blocking assignment here? Can we use blocking assignment here in the task reset?
Yeah, we can use blocking assignment also. That's not a problem. But mostly
Okay.
whenever we use the clock sequential logic circuit, we use the non-blocking, right? That's why.
Okay. Thanks.
And next, task drive. Here we are we are getting the data from the mailbox. In the generator, we will pass the data to the mailbox, right? Here we are getting the data from the mailbox and we are calling the write method. And then after that, we are calling the read method. So what are there in write method and read method? Here is the write method and here is the read method. So in write method,
How can I decide, ma'am? Repeat 5 times or 10 times?
yeah, you can,
There is
that is
any.
your wish.
Okay, okay,
You
okay.
can use 5 times or 10 times or 20 times. That's your wish. So in write method, if P select is high and next clock edge, if P enable is 0, then if P address equal to, we are just passing P write equal to 1, then P address equal to TR dot P address. That means transaction dot P address we are passing to the DUT. This TR dot address, TR dot write data we are getting from the generator class, right? That data we are passing to the address and the write data. And here we are passing enable as a 0, enable as a 1 in the first clock edge. And in the next clock, enable equal to 1, write equal to 1, P address equal to something, whatever the randomizer data is there, that we are passing to here, and write data also passing. Okay. And coming to the reader, select equal to 1, enable equal to 0, and write equal to 0 in first clock cycle or in second clock cycle. Whenever enable is 1 and by default select line is 1, right? When both are 1, we'll get the read data. So same happening here. Here also select is 1 by default because from second cycle only select will be 1. So enable will be 0 in the second cycle and then in third cycle enable will be 1. Okay, so how you will differ the cycle driver dot clock cycle and driver dot clock for every positive edge of the clock. So this is the driver. Driver is nothing but we will pass the data to the DUT. Right. So here we are passing the data. And then here main task we are calling the driver method here. Drive task method. And in the monitor, we will take the data from the DUT and we'll put into the transaction class. From the transaction class, we will send to the mailbox, and from that mailbox, we will get the data in the scoreboard, right? So same monitor also we have we have taken the path here via virtual interface and class virtual interface we have created, mailbox monitor to scoreboard created, constructor created, and task main, we have created the object for transaction class, and wait APB reset is high. we need to wait until reset operation is completed. Okay, once reset operation completed, after 2 positive edge of the clock, if write is high, if p write is high, then whatever the p address of interface, p write data, write data enable select all, we are sending to the transaction class. Okay, the monitor, you know the architecture, right? So this is the DUT, and from the DUT via virtual interface, we are passing to the monitor. So what happens here, monitor, it will pass to the scoreboard via a mailbox. So here it is passing to the transaction class and putting into the mailbox, and from the scoreboard, we will get the data. We will get the data from the scoreboard here. Okay, class scoreboard, and we need to create the memory here and created the function constructor and get the data in the scoreboard. Okay, you need to write the scoreboard logic also for checking the input, like expected data or not. Here we didn't return the expected code. Like that, after scoreboard, top is environment. In environment, what we do, we'll run all the task. Okay, we'll call all those tasks. So environment, we have created the generator, driver, monitor, and the mailboxes and virtual interface constructor, and we are passing the arguments to the generator, driver, monitor, because according to its connections. And in the pre-test, we are calling the driver reset task, and in the main test, we are calling the main task of generator, driver, monitor. Here we are using fork any, but you can you if you don't want to use fork join any, you can remove that. And in the main run test, we are using the pre-test method. I mean, calling the pre-test and the test method. So where are their pre-test and the test? Sorry, in the environment only there are pre-test and test, right? And top level of environment is test.sv. So here in the test.sv, we just need to create the environment and need to run the program. Okay, and here main top level, Testbench top level, we need to interface with the DUT signals as you have written in the Verilog HDL. Here test.sv. So this is the top level, and this is main testbench.sv. Okay, same program I will show you in UVM also, but I won't explain. You just go through that. Okay, see here in UVM how we have taken design. This is the design APB protocol slave design. Okay, this is the slave design. We have written somewhat differently here. Okay, by considering the p address plus 1, like that we have considered here, and somewhat differently. And APB interface, here we have written the interface, and from the UVM program, here for sequence, you need to start with a sequence. So just go through all these things. This is somewhat complex program. So how we have generated the APB sequence, and here different randomization constraints we have used. Okay, and sequencer. Okay, before, if you are not aware with the UVM, okay, before coming to the next session, just go through the UVM topics once. Okay, so that you will get some idea if you forgot anything, like what is meant by sequencer, what methods we use in the sequencer, and what methods we use in the driver and in the monitors scoreboard. Okay, just go through all these things. I will share this code also. If anyone interested can try. Okay.
Can you share the transaction.sv APB transaction? Just want to see. Third one.
Here in transaction, we have created address and the data logic, and constraint, one constraint we have used. And for each write data, we are passing write data inside. This is also type of
It is
constraint.
a kind of sequence item or anything else. Sequence item. It is a kind of a sequence item, no?
Yeah, it
Yes.
is different sequences. Yes.
Thank you, ma'am.
If we will try this code to understand, if any point we will stuck, then can we discuss this code
Yeah.
in the next
If we
session?
have time, after this, we can discuss.
Ma'am, hello.
Hello.
Yes, ma'am. You have written in the output signal, ready signal, like in the first design code. Yeah, first APB slave dot s APB slave dot p slave
Okay.
dot p. Yeah, here you are writing. You are giving the initial begin, you are giving the values for output signals in initial begin, right? But it is not synthesizable now, initial begin. It can't design a hardware implementation, right? It
It
can't
can't,
have any
we
hardware.
cannot design a hardware implementation, but in
Yeah.
Testbench wise, we can do force and release, right? So simply we are applying through the design, but in hardware, it can't do the synthesis. Only finite state machine it
Oh,
can, right? Okay.
okay.
So here you can observe the output. Okay. So what are the inputs and what are the outputs? I mean, write data and read data. See here. States here. Access is second state, third state, like that. And P address. This is the address signal and enable signal, and P read data and P ready signal, select signal, P write data, P write signal. So here P write data is high. If P write data is high, P write is high, it need to write the data, right? So what is the write data here? Initially 0, 42, 5A, 50, 48, 61. Okay. Once write is high, low, read, it should read the data. Okay. So here read address. Here is the read address and here is the read address and here is the read address. So what is the write address? So where is the write address here? The address.
But this
PR
is
data
not
is
as per.
yeah, read data. Hello.
Yes, Chad.
PR data is a read data, no?
Pure data is the read data.
PR data is data. X-axis is no. What does it assign?
Access and access wait state. States, those are states. Here P address, whatever write address, read address.
I think P address is the only signal, like it is both for both writing and reading. It is a common signal input.
Okay, see here. For B address, we are passing the value like 42. And for 11, 5A. For F, 50. And for E, 48. And for 12, 61. Okay. In the coming read side, read side, for 11 address, 5A. So here also 11 5A. And for 14, at the right side, we didn't taken any 14 as a address. That's why read data is X here, because no address at the right, right side. Okay, we didn't consider 14 address in the right side. And next E is 48. So here E is 48 and 11 is 5A. So here 11 is 5A. Have you clear with this? If you don't take the address, input address, then you can check this read data as a X.
If possible, could you please show the log? Means how this verification guys will be looking the log.
Log in the sense, the description here.
Yeah, that's what this one. Just wanted to understand this. That's it.
Okay, first of all, in UVM means you will get the info statement separately, warning statement separately, error statements, everything separately. Okay, but here we'll get all are combined. Okay, so first it will start with the driver, reset started and reset ended. In the generator side, we are generating this data. Okay, what data? P write is 1, P address is 11, P write data is 66. Like that, write equal to 0, 17, 90. Write equal to 0, 15, write data. So in each case, we are sending the address and data in this way. In the monitor side, here we are checking in the monitor. But actually, if you want to check what is the expected data, okay, in the logs mainly, we will check the expected data and the actual data. So how you will get the expected data and actual data? Based on the scoreboard logic.
Scoreboard.
You need to write the scoreboard logic, then you can check the expected data and the actual data. Okay. So based on your right, whatever you are passing the right data, you'll get the read data. In the monitor side. Okay. So just go through the session, everyone, the coding. So, and AHB, right? Everyone need to go through this block diagram. Okay, tomorrow we will discuss the bus transfers and all. Meanwhile, I will share the the spec and sessions also, recorded sessions. Okay, go through that recorded sessions and try to understand this basic like signals. What are the signals out there? Okay, once you understand the basic signals, we will discuss more on transfers. Okay, so transfers also I will share. Whatever the doubts you have, we can discuss here. Okay. So go through the transfers. I have explained very clearly in the session. Because all the things we can't discuss, right? That's why. Okay, I will share those, or from YouTube I will share later. Okay, is there any doubts up to here?
Ma'am, I have one doubt. Like as per specification of APB, in the write operation, the P selection and P write should be high at the same time. But in the waveform that we produce with this code, the P selection is high, and then after some time P write is high, and then P enable is high. So there's a difference of 2 clock cycle. If you open the waveform for this code, there is a difference of 2 clock cycles between P selection and P enable. That is one thing. And second thing is P selection is high, but P write is not high.
Here P selection is continuously high and P enable is high, low for each clock cycle. Okay, because always it will be not high, right? So P
Yes, that is true. But
Mm.
P selection is high means in the next cycle, P enable should also be high as per specification. If P selection is high, then in the next cycle, yeah, here the P enable should be.
Okay.
That is one thing.
What
And
about next signal?
second thing is P selection is high, then P write should also be high at the same time. Yes, right. According to
P write,
specification.
okay. Can you debug this where the like just a signal delays or mismatch, right? Can you debug?
Sure, I can check the code.
Oh, basically the selection is like just to say which master or which slave you are taking. Whenever the P rate is high, within the next clock cycle, P enable should be high. That's the spec protocol. That's the
Yes.
design. So
Yeah,
here
that's
you can
what
see
it
like
is.
whenever the P rate is high, then you should be next clock cycle the P enable. It doesn't
No,
depend
this
upon
is
P select or any
no,
other
it
thing.
should depend. I know, I will tell you why. Because here what is happening is you are setting P selection to high,